I'm Eric Knuth, a faculty member in mathematics education at the University of Texas at Austin. It's a pleasure to speak with all of you today. I would like to thank the organizers for inviting me, with a particular thanks to Dr. Lee and Dr. Na. The title of my talk today is Looking at Math Learning from a New Perspective, the Importance of Mathematical Disposition. Let me begin with a brief overview of what I will talk about today. First, I'll discuss the importance of the affective domain and its role in learning mathematics. I will be focusing on mathematical disposition in particular, as it plays a central role in the affective domain with respect to learning mathematics. I'll also discuss several critical areas involved in developing positive mathematical dispositions, as well as instructional strategies for fostering students' mathematical dispositions. And along the way, I will illustrate the ideas presented with various mathematics tasks. Although my talk is pre-recorded, and even with the large audience viewing today, I am hoping for your active participation as we think about the various mathematical tasks. First, let me begin the presentation with some good news. And this is something that I'm sure all of you are already familiar with. South Korean students' overall mathematics performance ranks among the best in the world. Fighting. If we take a look at results from the third International Mathematics and Science Study, the Mathematics Assessment, we can see that the Korean students score among the highest in the world. At both grade 4 and grade 8, we can see that South Korean students were the third best of all countries participating in the TIMSS assessment. However, despite their high achievement, similar to students from other top performing countries, South Korean students ranked very low with respect to their mathematical dispositions. And by dispositions, I include affective aspects like students' attitudes towards mathematics, in other words, their interest in math, how much they like mathematics, etc. Their views on the value of mathematics, whether it's useful in daily life, useful in other subjects, important to their futures, etc. And their confidence in their mathematical ability. So do they feel they do well in math? Do they think that math is one of their strengths, etc. If we take a look at the ranking of students' attitudes towards mathematics, so again, remember that's their interest in mathematics, how much they like mathematics, etc. We can see that South Korean students score near the bottom of countries participating in TIMSS. So in grade 4, they were second from the lowest, and in grade 8, they were the lowest scoring country. It's also important to note that as students progress from grade 4 to grade 8 rather, their attitudes towards math get worse. And we also see this reflected in the international average. In grade 4, it was 45% to 20% in grade 8. Likewise, we see very low rating of South Korean students with regard to their views toward the value of mathematics. So again, do they see it as helping in their daily life, provides future opportunities, it's a needed in other subjects? In this case, grade 4 data were not collected. But again, we see the South Korean students performing near the bottom. And finally, if we look at the ranking of students' confidence in mathematics, so whether they usually feel they do well in math, if they think math is easy, if they think they're good at math, again, we see South Korean students are not performing very well. In grade 4, they were second from the bottom, and in grade 5, fourth from the bottom. And again, we see as students progress from grade 4 to grade 8, their confidence in their mathematical abilities decreases. So this graph shows the general trend. When children first enter school, they typically have a very positive disposition towards mathematics. But as they progress in their schooling, their dispositions become more negative. This trend was also reflected in the TIMSS data, which showed a similar decline from grade 4 to grade 8. It's also important to note that middle school is a particularly pivotal moment in the development of students' dispositions towards mathematics, as negative dispositions really start to develop during this time period. So what do I mean by mathematical disposition? I view it as including confidence, flexibility, perseverance, interest, inventiveness, appreciation, and reflection and monitoring. It's also an inclination to see mathematics as sensible, useful, worthwhile, with a belief in diligence and one's own efficacy. And it's a combination of attitudes, behaviors, motivation, and interests. If you're familiar with the concept of growth mindset, you may note some similarity with disposition. So why do students' dispositions matter? A common assumption is that learning in mathematics is primarily reliant on the cognitive domain, where achievement and success depends on knowledge and skills. However, research suggests learning in math is dependent on both the cognitive and affective domains. Thus, dispositions play a crucial role in learning and can enhance or impede students' capacities to learn. Students' mathematical dispositions also affect their interest in and likelihood to pursue STEM, so science, technology, engineering, and mathematics related university majors and careers. And their mathematical dispositions also affect their willingness to engage, explore, grapple, and persevere with mathematical work. Thus, I hope it's clear that it's critically important that as teachers, we strive to foster positive mathematical dispositions with students. So the question is, how do we foster positive mathematical dispositions towards mathematics? Today, I will focus on 3 critical aspects that affect students' mathematical dispositions: sense-making, mathematical curiosity, and the practices of generalizing and justifying. Although I will talk about each aspect separately, they are integrally related to each other. That is, each one is influenced by and influences the others. So what is sense-making? I view sense-making as using one's mathematical knowledge strategically, flexibly, proficiently, efficiently, sensibly, etc., in order to reason about, make sense of, and to solve problems. Unfortunately, for many students, mathematics is often not a sense-making activity. Here are just a few examples of the kinds of things we often see students do. In the first example, students are given a problem: a bus holds 36 students. If 283 students are being bused to a museum, how many buses are needed? Many students respond 7.86 buses based on their computation, rather than correctly responding 8 buses. So for students, the fact that 7.86 buses does not make any sense, that doesn't enter into the mathematical problem. In the second example, we often see this from students when squaring a binomial. They square the first term and the last term, with the result being x squared plus 4 and missing the middle term. And in the third example, we might see students who are learning to operate with fractions, add the numerators and add the denominators together. So in this case, 1/2 plus 1/2 becomes 2/4. And again, lack of a sense-making perspective, a student should recognize that 1/2 plus 1/2 should make a whole, so 2/4 shouldn't make sense as an answer. Or likewise, they may see that 2/4 is the same as 1/2, and that answer still does not make any sense. So the point of these examples are that for many students, math is about following rules and procedures, not about reasoning and sense-making. So what can teachers do to foster student sense-making? In the next set of slides, I'm going to show two versions of problems that address similar content, but they require very different kinds of reasoning and sense-making. In this first problem, it's a typical textbook problem that students might encounter in which they're asked to multiply 3-digit and 2-digit numbers. In this case, students simply apply the procedure they've learned for doing 3-digit times 2-digit multiplication. A revised sense-making problem, which students still practice the skill of multi-digit multiplication, but they also have to reason about the problem in a non-trivial way. So in this case, students are asked to use each of the digits 1 to 5 exactly once in the 3-digit by 2-digit multiplication problem, and then arrange the digits so they get the largest product possible and the smallest product possible. A very different kind of problem compared to the previous one. In this case, again, students really need to think and reason through the solution. Here's a second problem. Students might be asked to find the mean of a set of numbers. Again, in this case, all students need to do is apply the learned procedure, add up all the numbers, and divide by how many numbers there are. But what if we revise the problem? In this new problem, they have the original set of numbers, and then they're asked, if we changed 87 to 92, how would that affect the mean? So how many students do you think would recompute to find the new mean rather than thinking about the effect of adding 5 to one of the numbers and realizing the mean would increase by 1 since there's 5 numbers and we're increasing one of the numbers by 5? Here's a few examples from algebra. The first two, students are asked to solve for x. And the third problem, students are asked to complete an XY chart for the function 2x minus 3. Again, these are pretty typical problems. Students only need to apply the procedure for solving equations or the procedure for computing the x and y values for a function. Not a lot of reasoning and thinking are required. What if we revise the problems? So in the first case, rather than asking students to solve the first equation, what if they're given the solution? They're told that x equals 1, and then asked to determine the solution to the following equation. 3x plus 4 minus 15 equals 7 minus 15. So in this case, the transformation is subtracting 15 from both sides of the equation. For many students, they go through and solve the second equation rather than just relying on the fact that the transformation has no effect on the solution, therefore the solution is still x equals 1. In the second problem, students are again given that the solution is x equals 1, and they're asked to determine the solution to the following equation. 3 times quantity x plus 2 plus 4 equals 7. So in this second task, the students see that the solution is x equals -1 without having to compute and solve the new equation. And finally, in the third task, students are asked to complete the xy chart for 2x minus 3, and then complete a second xy chart for the function g of x, which is 2 quantity x plus 2 minus 3. So in this third task, do students redo the XY chart for g of x, or do they recognize that all they need to do is add 4 to the y values in the first XY chart? Here's another problem, typical algebra task involving transformations. So if students are given the function f of x equals absolute value of x, for each of the following, explain the effect on the graph of f of x. So in the first case, the effect of adding a constant to the function. The second case, multiplying a constant by the function. And in the third case, adding a constant to the argument of the function. A revised sense-making problem is as follows. You are given two functions, f of x equals absolute value of x, and g of x equals a plus b times the absolute value of x plus c. And then they're asked, what must be true about a, b, and c if the graphs of these functions do not intersect? So the revised problem still addresses transformations, but again, in a very non-trivial way. And I encourage you, after the talk, to work through this problem. It's a very interesting problem. Here's another problem from algebra that requires students to think about the coefficient of the quadratic term and its effect on the behavior of a graph. So in this case, they're given the graph of the cubic polynomial, and they're asked to graph the function if the coefficient of the x squared term is changed from -7 to 5. A similar problem that addresses similar content, in particular transformations of functions. Here, students are given what looks like two identical graphs, but the graph on the left has a XY scale of -4 to 4, where the graph on the right, the scale has been changed to -2 to 2. And students need to figure out, how does that affect the coefficients of the different terms of the quartic polynomial? Finally, one last example. Here, students are asked to complete an XY chart with 5 points that are on the graph of the line below. In this case, all students need to do is understand how to identify ordered pairs for the line and put them into the table. If we look at a revised sense-making problem, again, students are asked to fill in the XY chart with 5 points that could be found on the graph of the following line. But notice in this case, there's no grid in the background of the Cartesian graph. So in this case, students need to understand the concept of linearity in choosing the points that could be on this particular line. So in terms of fostering sense-making, it's important to intellectually engage students so that they have a reason to think rather than simply apply a procedure without thinking. Problems need to be sufficiently complex or non-routine so that students cannot see the solution. Such problems also support making connections within and across mathematical ideas, a further means to strengthen students' understanding. And sense-making also instills a desire to know why, not just how, to do mathematics. When mathematical activity does not make sense to students, the result often leads to a negative disposition towards mathematics. Next, I want to talk about the second component of mathematical dispositions, mathematical curiosity. So what do I mean by mathematical curiosity? I define it as a desire to explore and engage with mathematical phenomena, an attitude, a way of thinking through a mathematical lens. So Pablo Picasso once stated, all children are born artists. The problem is to remain an artist as one grows up. In our case, as mathematics educators, it seems appropriate to say all children are born mathematicians. The problem is to remain a mathematician as one grows up. And I think as mathematics educators, all of us have this characteristic that we are mathematically curious. Unfortunately, for many students, that is not the case, particularly students at the secondary level. So what does mathematical curiosity look like? In the next set of slides, we'll look at mathematical curiosity in the context of several mathematics activities. Now, this is where I hope you'll participate with me in thinking about and doing some mathematics. So in this first problem, I want you to think about what observations and questions come to mind with the following sequence: 1, 1, 2, 3, 5, 8, 13, and so forth. Many of you may recognize this as the Fibonacci sequence. So I'd like you to think about it for a minute in terms of what observations and questions come to mind as you look at that sequence. Jot down some of your ideas and then share them with the person next to you. So I'm going to give you about 2 minutes to do this. So I know it wasn't a lot of time, but hopefully you had a chance to come up with a few observations and questions and share with people sitting near you. So I'm going to share, since I can't ask any of you to share some observations or questions, I'll share some of the observations that students have made when presented with this task. So what are the next several terms? What is the underlying rule? The pattern seems to alternate odd, odd, even, odd, odd, even, and so forth. So those are pretty basic observations that shouldn't come as a surprise. I've also had students notice the following. If you take the square of any term, that square is one less than the product of the preceding and subsequent terms. So for example, if we take the term 3, 3 squared is 1 less than 2 times 5. Or if we take 8, 8 squared is 1 less than 5 times 13. Or you may have noticed that the product of two adjacent terms is one more than the product of the preceding and subsequent terms. Again, for example, if we do 2 times 3, that is one more than 1 times 5, the terms that come before and after. Or if we look at 5 and 8, 5 times 8 is one more than 3 times 13. I'd ask you to raise your hand if you came up with any of these observations about the sequence, but since it's pre-recorded, I really can't see if you've got your hand up or not. So some initial considerations with these kinds of problems. At first, not every question or observation students think of will be mathematically interesting or productive to explore. Questions or observations will also likely vary depending on students' ages or their mathematical abilities. Students and teachers need practice. This isn't the kind of activity that students and teachers are used to engaging in. And sometimes you also need to think out of the box. And I'll show an example of what I mean. So what if the beginning two terms are not ones? So if we use the same underlying rule for the Fibonacci sequence, that is adding the preceding two terms to get the subsequent term. So in this case, if we start with 7 and 7, and then the sequence is 7, 7, 14, 21, 35, 56, and so forth. If we think about some of the prior observations, in this case, if we take any term and square it, it's 49 less than the product of the preceding and subsequent terms. So for example, if we take the second 7, 7 squared is 49 less than 7 times 14. Or if we take 21 squared, that's 49 less than 14 times 35. Some of you who are particularly mathematically curious may be wondering that 49 must be connected to the two starting terms, since 7 times 7 is 49. So let's take a look. What if the beginning terms are not 7s in this case, but what if they're 3s? What happens? So here, in this case, we get the square of any term is 9 less than the product of the preceding and subsequent terms. So again, 3 squared is 9 less than 3 times 6. Or 9 squared is 9 less than 6 times 15. Now we have the making of something we may want to explore more to see if that pattern continues to hold, and perhaps try to make sense of the relationship between the two starting numbers and the difference between the square of the term and the product of the preceding and subsequent terms. But we can also think about, what if the beginning two terms are not the same? So what if we have the Fibonacci sequence, but we start with 3 and 12, so that the new sequence is 3, 12, 15, 27, 42, 69, and so forth. In this case, the square of any term is 99 more than the product of the preceding and subsequent terms. So for example, 12 squared is 99 more than 3 times 15. Or 27 squared is 99 more than 15 times 42. So here we may be thinking, where does that 99 come from? It doesn't seem to be connected to the starting numbers of 3 and 12. And so that might be something we could explore with some different starting numbers. So the points I want to make thinking about these first two examples is that not every question or observation students think of needs to be explored. In some cases, the underlying mathematics may be too advanced, or it may not be important to explore further. For example, in the sequence starting with 3s, exploring why the square of any term is 9 less than the product of the preceding and subsequent terms may require mathematics too advanced for students. or further exploring it may not really matter. The point I'm trying to make is that simply posing such questions or making such observations is an important part of developing students' mathematical dispositions, and it's a part that students and teachers typically do not engage in. So let's look at another example. What observations and questions come to mind about the following equation? A squared plus B squared equals C squared. So here are several sets of triplets that satisfy the equation to assist you in your thinking. So again, think about this for a minute, jot down some of your thoughts, and then share with the person sitting next to you. And again, I'll give you about 2 minutes to do this. Hopefully you've had a chance to come up with a few observations or questions about that equation. Again, it would be great if I could call on you to share some of your thoughts, but since I can't do that, I'm going to again share some of the observations and questions that have come up in presenting this task to students and teachers. So did you think of every triplet appears to have one number divisible by 4 and one number divisible by 5. So for example, if we take the second triplet, 5, 12, and 13, 12 is divisible by 4 and 5 is divisible by 5. If we look at 8, 15, and 17, 8 is divisible by 4 and 15 is divisible by 5. Maybe you notice that if the first number is odd, the third number is equal to 1 more than the second number. So look at the first triplet, 3, 4, and 5. First number is odd, and 5 is 1 more than 4. Or perhaps the last triplet, 9 is odd, and 41 is 1 more than 40. You may have also noticed that if the first number is even, the third number is equal to 2 more than the second number. So in the only even triplet that I'm displaying, we could see that 17 is 2 more than 15. You may have also noticed that the third number seems to be of the form 4n plus 1. So for example, 17 can be rewritten as 4 times 4 plus 1. Or 41 in the last triplet can be written as 4 times 10 plus 1. What if we change the constraints of the problem? Rather than having a squared plus b squared equals c squared, what if it was a squared plus b squared is greater than c squared? Or a squared plus b squared is less than c squared? Then what do we notice? How does that change the nature of the triplets? Or if we think about it in a geometric context, with a squared plus b squared equals c squared being the Pythagorean theorem for right triangles, what's the geometric relationship when a squared plus b squared is greater than c squared? Or when it's less than c squared? What does that tell us about the type of triangle that may satisfy those conditions? So at this point, I want to stop here so that we could take a 5-minute break to stretch, and then we'll finish with the final part of the talk. Hopefully you've all had a chance to stretch and to continue working on the math problems. I'd like to now take you through a final math curiosity example. Keeping in mind, again, the point I made earlier, that posing these kinds of questions and making these kinds of observations is an important part of developing students' mathematical dispositions. So consider this problem. ABC is an equilateral triangle, and points D, E, and F are its midpoints. What observations and questions come to mind? So again, I'd like you to think about it for a minute, jot down some of your ideas, and then share your thoughts with the person next to you. So again, I'll give you about 2 minutes, which I know is not very much time, but hopefully you'll have enough time to just discuss a few of the ideas and observations that come to mind. So hopefully you had a chance to think about observations and questions that might come to mind and share those with the people near you. So you may have thought of some of the following questions. What is the area of triangle DEF relative to triangle ABC? So certainly visually, looking at the figure, it appears that triangle DEF would be 1/4 the area of triangle ABC. But can we show that mathematically? You may have asked, is triangle DEF also an equilateral triangle? And if you think it is, can we prove that it is indeed an equilateral triangle? These are pretty typical problems that you might find associated with this in a geometry textbook. But what if we loosen the constraints? For example, what if D, E, and F are not located at the midpoints? In this case, how does the area of DEF compare to the area of ABC as a function of the location of vertices D, E, and F? So instead of halfway, what if D was 1/3 of the way along segment AB, and so forth? So we can see here, as we move the location of D, E, and F, we might be thinking about what's the function that describes how the area of the inner triangle DEF relates to the area of the original triangle ABC as the vertices change. And we can see that in this case, the function that describes the ratio of the two areas of the triangles as the location of the vertices vary is the quadratic function 3x² minus 3x plus 1. And hopefully the trace shows up that you can see that dot is tracing out the ratio of the areas as a function of where the vertices are located. And for those of you who are particularly mathematically curious, you may also wonder whether there's any significance to the coefficient of 3 and the number of sides of the figure. The coefficient of 3 and the triangle has 3 sides. So we might think about that. What if the polygon is not an equilateral triangle? What if we consider other regular polygons, like a square or a pentagon? So again, in each case, how does the area of the inner polygon compare to the area of the outer polygon as a function of the location of the vertices? We might also ask, what if the triangle is not an equilateral triangle? In this case, for just a general triangle, how does the area of the inner triangle compare to the area of the outer triangle as the location of the vertices changes? Interestingly, the function is the same for every triangle. That is, 3x² minus 3x plus 1 describes the ratio of the areas as a function of the location of the vertices. I'll leave it to all of you for homework to see if you can show that that is actually the case. So fostering mathematical curiosity requires teachers to ask students to make observations about mathematical phenomena. Asking students to pose and even sometimes explore what-if types of questions. It's also important that as teachers, we discuss with students what makes a mathematically interesting observation or question. Perhaps start with including mathematical curiosity problems as warm-ups or lesson openers, and build such activities into a more regular part of instructional practice. Because it's not something that students are used to, it really requires a consistent and regular effort to make it become part of their regular classroom practice. As Mason, Burton, and Stacy noted, there is nothing wrong with being unable to make progress on a question, and there is tremendous value in tussling with it, rephrasing it, distilling it, mulling it over, and modifying it in various ways. Also, as Brown and Walter noted, coming to know is not a spectator sport. Those standard textbooks, especially in mathematics, and traditional modes of instruction may give that impression. Coming to know is a participant sport. Students often do not experience the messiness of mathematical activity, and engaging students in these kinds of tasks is one way of engaging students in this mathematical curiosity and the messiness of mathematical activity. Finally, I want to talk about the practices of generalizing and justifying, the third of the critical aspects of mathematical dispositions. So again, what do I mean by generalizing and justifying? I define these as noticing regularity, patterns, and structure in relationships among mathematical phenomena. That's the generalizing part. And seeking to understand the mathematics underlying these generalized relationships. That's the justifying part. I think these two are inseparable, and that's why I have them together. That engaging in these generalizations naturally involves then trying to figure out why these generalizations are true. Similar to the other two aspects of mathematical dispositions, I'll go through a series of tasks to illustrate some of these ideas. So here's an example of a generalizing activity from an early algebra class. So if you fold a piece of string to make one loop, while it's folded, cut across the loop, how many pieces of string do you have? So you can see in the figure, the red being the string. If you cut, you end up with the two extra pieces and then the folded piece. So you can imagine fold another piece of string to make the loop and make two cuts and find the number of pieces. And then 3 cuts, 4 cuts, and so on. What do you notice? So again, take a couple minutes to think about this, share your thoughts with the person next to you about any generalizations that you make, and maybe even if you have time, how you might determine and justify those generalizations. hopefully you've had a chance to come up with some generalization and also maybe even thoughts about how you might justify that generalization. So one of the generalizations, the justifications that we've noticed with students that has come up is keeping track of each cut and how many pieces. So one cut, there were 3 pieces, 2 cuts, 5 pieces, 3 cuts, 7 pieces. And if you generalize to n cuts, you get 2n plus 1 pieces. One of the important things is to see the structure in this problem where one can connect the generalization to the problem situation. So here we can see that each new cut produces 2 new pieces. That's the 2n. And there's always the one folded piece, the plus 1. One possible approach to justifying why the generalization must be true. The connection here of sense making as students seek to understand why justifying and through justifying. If we take a look at a second activity. So here you're told that the sum of 5 consecutive integers is divisible by 5. So for example, 2 plus 3 plus 4 plus 5 plus 6 equals 20, and 20 is divisible by 5. The question is, will this always be true for any 5 consecutive integers? So again, think about it for a minute, explore it, come up with your generalization, and think about how you might justify it. Again, I'll give you a couple minutes to work through this. Again, I hope you had a chance to explore the problem a little bit and come up with your response to, will this always be true for any 5 consecutive integers? And I suspect for many of you, you found that does seem to be the case. So how might we justify? So one way might be to rewrite the sum of a particular example as 3 minus 2 plus 3 minus 1 plus 3 plus 3 plus 1 plus 3 plus 2, which simplifies to 5 times 3, and this product is divisible by 5. We could consider this to be a generic example, as the particular 5 numbers we're adding together doesn't make any difference, as this approach would hold for any 5 consecutive numbers. Or we might take an algebraic approach, as in the second justification. In this case, the algebraic expression simplifies to 5x, which is, again, divisible by 5. Here again, we see the connection to sense-making as students seek to understand why through justifying. By generalizing plus, I'm making the point that we also see a connection to mathematical curiosity by asking what-if type of questions and to sense-making as students try to understand why through justifying. So we might ask, what if we consider other odd numbers? When k is odd, is the sum of k consecutive integers divisible by k? Or we might ask, what if we consider even numbers? When k is even, is the sum of k consecutive integers divisible by k? In the case of this particular problem, the key insight is that for any sequence of consecutive odd integers, there's always a middle number. So k consecutive integers will always be divisible by k when k is odd. Let's take a look at a second problem. So here we're told some numbers can be expressed as the sum of consecutive numbers. For example, 6 can be expressed as 1 plus 2 plus 3. 11 can be expressed as 5 plus 6. And 18 can be expressed as 3 plus 4 plus 5 plus 6. So the question is, which numbers have this property? So again, I want you to take a couple minutes to think about this. Can you find other numbers that can be expressed as the sum of consecutive numbers? What numbers seem to have this property? What numbers don't seem to have this property? So again, take a couple minutes, jot down some of your ideas, and share with the person sitting near you. I'm sure you've come up with various generalizations and observations about this particular problem. So here are several generalizations to explore and justify, and I'm sure all of you came up with others as well. So it appears that odd numbers can be expressed as the sum of consecutive numbers. So 7, for example, is 3 plus 4, 9 is 4 plus 5, and so forth. Perhaps you notice that powers of 2, so like 2 to the first, 2 to the second, 2 to the third, cannot be expressed as the sum of consecutive numbers. Perhaps you saw that even numbers that are not powers of 2, such as 6, 10, 12, 14, 18, etc., can be expressed as the sum of consecutive numbers. And maybe you've even noticed that some numbers can be written in more than one way. 15, for example, can be written as 7 plus 8, or it can be written as 4 plus 5 plus 6. So as a side problem, we might investigate what numbers can be expressed in more than one way. With all these generalizations, there's the need to try to figure out why. And that's where, again, kind of the sense making and justifying these generalizations come into play. For time and just to give you some homework, I'm going to leave justifying these generalizations to all of you as homework, and knowing what good students you all are, I'm sure you'll complete your homework. So fostering, generalizing, and justifying. So it's important to foster students' abilities to notice regularity, patterns, and structure in relationships among mathematical phenomena. That's where generalizing plays a central practice. It's also important to engage students in seeking to understand the mathematics underlying these relationships. This is where sense-making comes into play as students seek to understand why a particular generalization seems to hold. Generalizing and justifying are core activities of mathematical practice and play a critical role in the development of mathematical dispositions, and also are connected and interrelated with justifying and generalizing, are interrelated with mathematical curiosity and sense-making. In closing, I want to note that not every problem or question posed to students needs to reflect the types of problems I presented. But students do need to regularly engage in such activities. So I think it's important to strike the balance between engaging students in these more open-ended, sense-making, mathematical curiosity, generalizing and justifying types of activities, balancing that with the need to do some of the other types of activities that students regularly engage in. But the point is that they do need to engage in these kinds of activities that I've been sharing on a more regular and consistent basis. Supporting students in developing and maintaining a positive disposition towards mathematics requires a consistent grades K through 12 effort. That it can't just happen in a particular grade level or middle school or high school, that it really needs to be consistent so that we can build on students' early mathematical curiosity and positive dispositions when they enter schooling, and maintain and sustain that level of positive mathematical disposition. So again, learning is dependent on both the cognitive and affective domains, and dispositions can enhance or impede students' willingness as well as capacities to learn. I believe it's critically important to students' mathematics learning to possess a positive disposition towards mathematics, something that I believe has not received enough attention in teaching mathematics. In this talk, I focused on the affective domain and 3 types of mathematical activities that play a role in fostering students' mathematical dispositions. I hope that you leave the talk with some new ideas to think about as you go back to your classrooms. By fostering students' sense-making and their mathematical curiosity, as well as engaging them in the practices of generalizing and justifying, their mathematical dispositions can remain positive throughout their K-12 mathematics education. In case you're interested in reading more about some of these ideas that I've talked about today, here are several references you might find interesting. A book on Art of Problem Posing by Brown and Walter, a couple of my own articles about mathematical curiosity, a book by Mason and colleagues, Thinking Mathematically, and a book by Silver and colleagues, Thinking Through Mathematics. I know there'll be time for questions and my responses following this talk. And so I look forward to the questions and look forward to having an opportunity to respond to some of your observations and comments. Kamsahamnida.